Hello and welcome. So it says change the given expression into vertex form by completing the square. Well, when we're looking at this, the vertex form isn't really what matters. Completing the square is going to be the bread and butter of what we're going to be doing. Vertex form is the format where we end up with something squared, potentially plus a number in front. Maybe there's another number in front of that parenthesis, right? That's the main, and you get vertex form. That's a natural follow by completing the square. The whole point of completing the square is to getting a perfect square trinomial, and that is the crux of vertex form, right? So that's all we're going to be doing for this problem is completing the square. So looking at this lovely gem, let's kind of analyze it a bit. There's usually a few ways to complete the square. And the biggest difference between what we're going to do is asking if we have an equation to work with or if we don't. Now, and what an equation is if we have an equal sign in the problem, right? Equals 0 or equals a number, that would be an equation. What we're given here is no equal sign. This is called an expression. And what this means is that we aren't allowed to add a number in. If I want to add 5 to make the perfect square trinomial, well, you can't just add 5 because there's no other side to do it to keep equivalence, right? There is only our expression here. So that means that you would have to also subtract 5, or in other words, right, add 0 in order to keep equivalence. So just keep an eye, expressions are a little more tricky, which is why we're going to go through this together. All right, so to start this out, we'd say, all right, so completing the square requires that our very first number, the number in front of our x squared, is a 1. It's currently not a 1. Well, the only way that we could take that out would be division, but what we do to one side, we do to the other. We don't have an equal sign to divide with. So how we're going to take it out is we're going to cheat a little bit, and we're going to use a greatest common factor. Factoring is the closest thing you get to division closest thing you get to division by keeping the equivalents in. So we're going to pull out 5. And you're thinking, whoa, hold on. That's not divisible by 5. Well, that's okay. So when we're looking at this, we're going to imagine 5 divided by 5, that'll give us 1x squared, right? That's all taking the GCF does is it divides by a 5 there. So if I want to take 5 out of this, that's like division of 5. So you get plus 3/5 x. Oops. There we go. All right, and then our last term, division of 5, so plus 2. All right, and this keeps the equivalence. If I were to take that 5 and distribute it back out to the entire expression here, we get to the original problem, and that's the point of factoring, right? We haven't actually changed anything. We've just made it a little easier for us to work with completing the square. Okay, so now that that's a 1, huzzah, that's what we want, that's what we need. So this 5, all we're going to do is we're going to keep bringing it down through the entire problem. I'm going to switch those parentheses to brackets just to make it a little easier to see when we get other parentheses in our expression. So first off, we have the x squared plus 3/5 x. I'm going to scooch over that 2 a little bit. Now to complete the square, I need to add a number in to create the perfect square trinomial. And that number is going to come from our middle term here. So if I take 3/5 and I half it, well, half of a fifth is a tenth, so 3/10 is what we're going to end up with there. And that doesn't simplify, so huzzah. So I'm going to take that 3/10, and now I'm going to square it. Well, that's just 3/10 times itself, so 3 times 3, 9, 10 times 10, 100. All right, so these two numbers, right, these are what we need to complete the square. When you complete the square, you get a lot of really cool patterns, and the first pattern is our squared number here is the perfect square, right? It was a squared number, so the perfect square needed to complete the square. So if I were to factor this piece alone, you will end up with a squared parenthesis, right? And you'll have x, and then plus, that plus is coming from the same sign as our middle term. And what's really cool is that the number we got the perfect square from, our 3/10, that is the number that goes inside that parenthesis there. And this is always going to be true pattern-wise. So once we find half of the middle number, right? That's the number in the parenthesis, and squaring that is the number needed to be added to our expression to get to that parenthesis, right? And then there we go. So that's what we needed to add. So now we say, all right, so now I've added the number I needed. We've got to keep equivalence. Once you add that number, because there's no equal sign, we have to also subtract that number. So technically, all we've added here is 0. Okay? Now, again, this is the piece that goes into the parentheses here, which means that on my next line, right, the 5 that was in front, yeah, that 5 is still there. And then we still have two numbers we didn't use, which is the -9/100ths and the 2. Those combined together, all right? So just kind of off to the side here, 2, if I wanted to get a comma denominator, that would be 200 over 100, right? That is 2. So substitute that in, all right? So then we get 200 minus 9. Should be positive 191, I believe, over 100. And there we go. We have technically finished completing the square. Now we just need to simplify it, right? We have that parenthesis squared. We have the number after. Like, everything's kind of looking up for us, right? So our last step to simplify it is that this like awkward extra set of parentheses, right, this 5, we just need to finish distributing that. So if I had like a 5 to an x plus 1, right, it would multiply to the x to give you 5x. It multiplied to the 1 to give you plus 5, right? Here's our first term. Here's our second term. And that 5 distributes going to go to the first and to the second. All right, so when we multiply it to the first, that 5 is just going to start, oops, let me write that a little nicer. 5 is just going to go in front of that parenthesis. Right? Because of PEMDAS, because of the order of operations, we cannot, right? We cannot multiply before the exponent is gone, right? So we can't bring the 5 into the parenthesis until after that square is gone. But the whole reason of completing the square is to get a parenthesis squared. You're not removing it. We're just going to put the 5 in front, and that's totally fine. All right, for the second one, all we're doing is we're doing the plus 191/100ths times 5. That's technically a 5 over 1, so it multiplies into our numerator here. Okay, and then we just need to simplify this. All right, so I'm going to write this off to the side, 191 over 100. Right, this is the same thing as 191 over 5 times 20. Right, 5 times 20 is 100. I just rewrote that. So if we're doing 191 over 100, right, which is our 5 times 20, and we're multiplying that by 5, technically that 5's in the top, but we also have a 5 in the denominator, so those cancel, and we're left with 191 over 20. So that means our final answer here is 5 times the parentheses of x plus 3/10 squared plus 191 over 20. Final answer. Right? We have the squared parentheses. Everything's been distributed. Right? Simplified as much as possible. That is a completed square. Thanks for watching.